This is section 5.2. We're exploring quotients of polynomial functions. So that's when we take one polynomial function and we divide it by another. We get, down here it's defined as a rational function. So it's a function that can be expressed as f at x, which is equal to p at x over q at x, where p and q are polynomial functions. So what does that mean again, just as a review, what a polynomial function is? Who remembers? So p and q have to be polynomial functions. Yeah, Margot?
It has to have a positive whole number exponent.
Yep. Right, so no square roots anywhere, because those would be not positive whole number exponents. Those would be fraction exponents. Okay, so as an example, we have f at x here. We have 3x squared minus 1 over x plus 1. And it's important to identify the limits to these equations now too, because we have denominators. Remember, you can never divide by 0, so you always have to be aware of that whenever you're working with these quotients. So you have to make those restrictions. X cannot equal -1, because if it is here, you're going to get 0 on the denominator. And the other one, f at x is equal to 1 minus x over x squared. Again, you have to specify that x cannot equal 0, because if you did, you again would have a value over 0. But f at x, this is not a rational function because we have that square root in the denominator. Okay, any questions about that? What rational functions are? Okay, so we're going to explore some of the graphs created by dividing polynomial functions. So the first one we look at says, what are the characteristics of the graphs that are created by dividing two polynomial functions? So using the given functions, write the equation of the rational function y equals f at x over g at x. Enter this equation into your graphing calculator and graph it using the window settings shown as the sketch. So this y f at x over g at x, we're looking for in example A. So this would be x plus 1 over 1 minus x squared. Okay, and whenever you can, and you should, look for scenarios where you can factor, you should do so. Okay, because that's gonna help you out down the road. Here we can see that this is actually a difference of squares on the denominator. It's 1 squared, 1 minus x squared. So we're actually gonna have 1 minus x, 1 plus x. Okay, and then you could actually cross these out and you have 1 over 1 minus x. So we should have a really good idea of what that graph looks like, because it's quite close to a parent function 1 over x. In any event, you should always look for the opportunity to factor and to cancel values out. All right. So I'm going to show you the graph now. Okay, so here's the first graph. X plus 1 over 1 minus x squared. And again, of course, it does look like, as I mentioned, that parent function just with a horizontal shift of 1 unit to the right. Okay? And that's because of that being factored and those values canceling out. So the question B reads, zoom out here. Describe the characteristics of the graph you created in part A by answering the following questions. So where are the zeros? So, are there any zeros here in this graph? No, so there's none, right? We're going to put none here. Okay, and that's because we don't cross through y equals 0. There's actually a horizontal asymptote. Okay, we also know that from the parent function. And the reason why is because it's 1 over x is our parent function. If x is 0, that's undefined, so there's no zeros. Are there any asymptotes? If so, where are they? So yes, there's a horizontal asymptote at y equals 0. Okay, we have a horizontal asymptote at y equals 0. We also have a vertical asymptote at x equals 1. Okay, it's right here. Okay, and why would we have that as a vertical asymptote? Because remember, again, the function looks like this. We have 1 minus x squared. If x is equal to 1, well, we're going to have a value over 0, which is vertical asymptote. Okay, so we see it graphically, but we can also see it algebraically. Any questions about that so far? Okay. What are the domain and range of the function? This is easy. Domain is x can equal 1. Everything else is fair game. And range is YER, all possible values. Oh, sorry, not y. Not y equals 0. So domain. Okay, there's our domain and range. Next, is it a continuous function? Who can tell me? Yep. No, it's not, because there's an asymptote. Okay, that goes through the middle, so it's not a continuous function. There's also the horizontal asymptote. V. Are there any values of y equals f at x over g at x that are undefined? What features of the graph are related to these values? There definitely is. So we're going to say yes. And what are they? Yep. Yeah, there's the vertical asymptote at x equals 1. Sorry, there's also, it's very difficult to see, and part of the reason I missed that, you might have missed it, I zoomed right in. And this is almost impossible to see. But there's also, you get a better idea. You actually can see it much better on the screen than on my piece of paper. And you get a better idea if you were to use a graphing calculator. But right there, at x equals -1, there's a hole. Okay? And I appreciate that this is virtually impossible to see. If you were to use your phones and graph it on an app, you would see clearly at x equals -1, there's a hole. Why might that be? Let's think algebraically now. Yeah, Anthony. Sorry? Yeah, it's undefined there, right? And the reason for that is because if we take x equals -1 and plug it in here for x, we're going to get an undefined value. We'll actually get, if we say at x equals -1, we get 0 over 0. It's a little close. You guys see that algebraically? So what happens when we get 0 over 0? What happens on a graph? We get a hole. Okay? So that hole then needs to be considered in the domain and range as well. Okay, so this, when I go back here to my domain and range, x can also not equal -1. Okay? And likewise, if x can't equal -1 and there's a hole there, I have to take into consideration the y value then there. So my y value cannot equal 0, but it cannot also not equal 1/2, so 0.5. And the reason for that is, let's see if you can see that. Range. No. So sorry, that is also a reason why the graph is not continuous as well, right? Because of that hole. Okay, that's the reason why it also is not continuous. So where the values are undefined, yes, we have a vertical asymptote at x equals 1, and then we have a hole at x equals -1. Okay, any questions about when there's a hole or when there's a vertical asymptote? So vertical asymptote occurs when we have a number over 0, and a hole occurs when we have 0 over 0. Any questions about that? Okay, describe the end behaviors of this function. So as x approaches infinity, y approaches 0. As x approaches -infinity, y approaches 0. Okay? Is the resulting graph a function? Explain. I think we can say unanimously yes, right? Because of our vertical line test. Okay, if we draw a vertical line anywhere on this graph, we're only going to cross through 2 points. And that's ensured that it happens because at x equals 1, when the graphs might overlap, there's actually a vertical asymptote, so they never do, in fact, overlap. Okay? Yeah, Alex?
So for the range, why'd you put it can't equal, how'd you find out that it doesn't equal like 1/2 if when you plug in -1 it's 0?
Yeah, I'm trying to figure that out myself. Y is equal... I'm going to look at the next example. They have here y cannot equal 1/2. And if we look at the graph, well, let's plug in 1/2 for y. I'm not sure why. I don't know if that's a typo there. Let's see. If we plug in 1/2 for y, let's try it. Let's go up here. So 1/2 is equal to yeah, I have no idea. X would be -1.
Let's just calculate 5.
Yeah, and it can't be -1, so that's why. All right, so let's explain that one more time. So, it's a very good question. The range is y cannot equal 0, but it also cannot equal 1/2. And the reason why is when y is actually 1/2, which we tested here. So I plugged in 1/2 for y, and I solved for x. X was -1. Okay? And so if x is -1, it's undefined. Okay, so it's strange, but the only way it worked algebraically is once I made this cancellation out, because otherwise we ended up with 0 on the numerator, right? Because I was able to factor this out and cancel it, I was able to determine the value that x is still actually -1 when y is 1/2. Okay? Yeah, hopefully it'll make a little more sense with some other examples, but you have to kind of consider, you know, the original equation and the value of x as being -1 here. But when you factor, you can cancel these values out, and actually your numerator will have a valid value. So this is similar to, like, you know, when we're using the difference quotient and we use the value of h, we can't just plug in h for 0 right away. We have to do all of the algebra, then cancel the h's out, and we can solve for the limit. You guys remember this? When we use the difference quotient? Remember that? As h approaches 0, and Luigi suggested originally, he said, well, why don't we just plug in 0 for h initially? And what we got was we had 0 over 0, so it was undefined. So we actually had to work out the values of h and then cancel them out. And then it worked. You guys remember that? Then we can plug in the value of h? You don't remember that? Okay, well, it's the same idea. Luigi, do you remember that?
Yeah.
Okay, so it's the same idea. You actually can cancel these values out once this bottom term is factored, and you can figure out that at y equals a half, x is -1. Okay, Alex?
So on a test, there's a hole, you just have to keep plugging in the y values to see which gets -1.
No, you would have to factor the original quotient function like this, just like I did. Okay, and then you could solve.
Oh.
Right? So another very good question, Alex. So let's go back. Let's say we didn't know it was a half, right? We have this scenario, okay? We're going back to the original question here. You know, and the question that Alex might have is, well, how do I know what the range is then? The only reason we figured it out last time is because we had the answer, which we saw was a half. If I have this, I need to factor it. Does everybody understand how I went from there to there? Yeah. Okay, so once I do that, everyone understands that these can cancel and I have that, right? Yes? Okay. So once I have this now, knowing the fact that once I cancel values out, it behaves differently than plugging in initially. Now I plug in. So plug in the value of x equals -1. Now when I plug in that value, I get y is equal to 1/2. Okay, does everybody see that now? How you can figure it out with the original equation? Okay? All right. Okay, letter C. Write the equation defined by y is g at x over f at x. Predict how the graph of this function will differ from the graph of f at x at g at x. Graph this function using your graphic calculator and draw a sketch. So we're just reversing them now. So we're actually graphing 1 over x squared over x plus 1. Okay, so again, if I were to factor this, I could say y is equal to 1 minus x, 1 plus x over x plus 1. These cancel. Y is equal to 1 minus x. So if I wanted to predict the way this looks, very simple, right? Y-intercept is 1, negative slope of 1. Okay? So that's what that graph looks like. So you can see it here. Okay? Now the other thing you need to be aware of is, again, at -1, we're going to have a number. Sorry, we're going to have 0 over 0. So at x equals -1, we have 0 over 0. So we actually have a hole there as well. And it was actually a little bit easier to see this time. I just drew right into it, but there is a hole there. Okay?
What?
Yeah. I just plugged up the hole, but yeah, there is a hole there. Okay? And this again would be discontinuous. Okay, because of that hole. Describe the characteristics of the graph you created in part C by answering the questions in B. So if we were to answer all the same questions from B, what are the zeros? So there is a 0 here. It would be at x equals 1. Okay, so why is that a 0 now? So we have x equals 1. we're going to have a number so to find out the zeros, we set, of course, y equal to 0, and we solve for x. If I set y equal to 0 here, careful, Kate, some of you might say, well, this is undefined. It's not undefined. I can multiply both sides by x plus 1. These cancel. This still becomes 0, so I have 0 equals 1 minus x squared. And then I have x squared is equal to 1, x is equal to plus or minus 1. And actually, we don't have a 0 at minus 1. So again, before you would plug in this, you would want to factor this side. See how I'm multiplying this out before I've canceled it? So it doesn't actually work when you plug in the y value before you factored the other side. So let's do that again. So I have 0 equals 1 minus x, 1 plus x, over x plus 1. These cancel. Now I have x is equal to 1. Okay? So there's my 0. So this is 0. This is x value. X value when y is equal to 0. Is this a continuous function? No. Are there any values that are undefined? Yes, at the hole. What are the features of the graph related to these values? There's a hole there. Describe the end behaviors. As it goes to infinity, it goes to negative infinity goes to positive infinity. Is the resulting graph a function? Yes. Any questions about either of those two? Okay, we'll do it for one more. They do it for a lot. You can see here in F, we actually do 8 examples. So you can imagine how long that would take. Let's choose one more. Any preference to the one you guys want to try?
The last one.
The last one? Sure. Okay. So we're going to look at 8. 2x squared minus 3 over x squared plus 2. Alright, so the first thing we want to determine are the zeros. Okay. So zeros again occur when the y value is equal to 0. Okay, but before we do that, we want to see if we can factor and make any cancellations out of this. We've learned that we need to do that first. 2x squared minus 3 x squared plus 1. There's nothing we can do here, right? There's no factoring that you guys can see. Okay, so we'll just set that equal to 0 then. This cancels. So we have 2x squared minus 3 is equal to 0. 2x squared is equal to 3. X squared is equal to 3 over 2. Okay, so our zeros then occur at plus and minus root 1.5. Yep.
So you multiplied the bottom out? Or?
Yeah, so I multiplied both sides by x squared plus 1. And so the bottom, this still becomes 0, and this cancels. Okay? You can do that, right? Yeah. Some people want to go and say that's undefined. It's not quite undefined. So there are our 0 values. What is that? Just give me a decimal value. Plus or minus square root of 1.5.
Yeah.
1.2247. Okay. All right, next one. Are there any asymptotes? So, how are we going to determine if there are any asymptotes? Remember, an asymptote is when we have a value over 0. Okay? So, what value on the denominator could give us 0? Is there any value of x that could give us 0? No, no value of x. Okay? So, we would say no vertical asymptotes. Okay? Now, for horizontal asymptote, how would we figure out a horizontal asymptote? What worked in the past? Where did we get horizontal asymptotes before? We had y equals 0 for this one. There was a horizontal asymptote. Anybody have any ideas? Horizontal asymptote? Okay, I know there's a horizontal asymptote at y equals 2. Okay? And the way I know that is, yeah, Daniel?
You divide the degrees?
Yeah, you divide these degrees out, right? That's in the summary. And that's actually a conclusion that we get to through the process of this investigate. What we actually learn from our graphing calculator is that there's horizontal asymptotes every time the degree is the same in the numerator and the denominator. You divide the coefficients, okay? So I can't give you one example and show you how to calculate the horizontal asymptote. The point of today's lesson and going through 8 different examples is to come to that conclusion. Okay, so let's just go back and I'm going to quickly go through the different graphs and show you. So for this one, IV, if you were to use a graphing calculator, what you'd see is there's a horizontal asymptote at y equals 1. Okay, and the reason for that is because the degree of the numerator and the denominator is the same. It's 1. So you divide the coefficients, 1 divided by 1. So there's a horizontal asymptote here at y equals 1. Okay? I can't give you a better explanation than that, because that's the point of why this is so long, is because we graph them all using graphing calculators, and we recognize patterns, and then we make conclusions from those patterns. Okay? Joseph?
When the degrees are not the same, there could still potentially be a horizontal asymptote, right? Just not at a given number.
No, there's what they call an oblique asymptote, which is an angled line. Okay? And we're going to show you that as well. I'm going to show you that in a second, okay? But I just want to show you this graph. So 4 here, we have x over x. Those are the leading degrees, okay? When I say degree, it's the highest exponent, right? That's what I mean by that. The highest exponent in the numerator and the highest exponent in the denominator. In this case, it happens to be 1 and 1. You divide the coefficients and you get 1. So on the graph IV, which is here, you'll notice that there's a horizontal asymptote at y equals 1. Okay, does everyone see that? Okay, let's look at another one that has the same. Okay, that's it. So we're on to the one that we're doing right now. We have an equal degree in the numerator and the denominator. The degree is 2. Remember, it's the highest exponent. We divide those two terms, the coefficients, so 2 divided by 1. So there's going to be a horizontal asymptote at y equals 2. Okay, so if we look at the graph, you'll see at y equals 2, right here, it's not immediately obvious, but there's a horizontal asymptote that runs through there. Okay? Alex?
It has to be the highest degrees?
Yes, it has to be. All the other numbers don't matter. Okay? Now let's look at V here. We have this happening. Okay, there's a line that goes through here that you can see both sides of this function approach it. Okay, so this is called an oblique asymptote. And all oblique means is an angled line. Okay, not a horizontal line, not a vertical line. It's a angled asymptote. Okay, they call it an oblique asymptote. So let's see what's going on if we look algebraically for V. So what we notice is that the numerator has a degree 1 higher than the denominator. If that's the case, you divide the coefficients. Sorry, you divide the binomials and you're going to get an oblique asymptote where the equation of that line ends up being, so x squared plus 1 over x minus 1. So it says here, for the purpose of this chapter, students not expected to find equation. Not yet. Okay, we will learn later in the textbook how to find the oblique asymptote equations, but for now, we're not going to learn the equation. All we need to know is that when the degree is higher in the numerator than it is in the denominator, you're going to get an oblique asymptote. Okay, so same thing in VI. Again, we have the numerator being 1 degree higher than the denominator, and we get an oblique asymptote, which is here. Okay, so let's look through the other ones. We have numerator is 1 degree higher than the denominator in I. Not sure why that's just a straight line. This horizontal asymptote, this one. So when your degree in your numerator is lower than your denominator, degree in your numerator is lower than the degree in the denominator, you don't have any asymptotes. Okay? And that makes sense because we can never get 0 in the numerator in this case, right? There's no value. 3 is always going to be 3. It's a constant. So again, I'm going through the different examples and I'm looking for the patterns. And that's basically what the investigate is, right? We graph all of these on a graphing calculator. We come up with the graphs and then we identify the patterns. So here's an interesting situation. When we have the denominator of a higher degree than the numerator. Denominator has a higher degree than the numerator. Denominator has a higher degree than the numerator. You're going to have a vertical or a horizontal asymptote at y equals 0. Okay, so that happened in the very first example. Here, the degree of the denominator is what here? In this example, it's 2. What's the degree of the numerator? 1. So when the degree of the denominator is higher than the numerator, you have a horizontal asymptote at y equals 0. Okay? Here we have the degree of the numerator is higher than the denominator, so we don't have a horizontal asymptote at y equals 0. Here again, we have the degree of the numerator higher, the denominator higher than the numerator. We have a horizontal asymptote at y equals 0. And here again, VII, the degree of the numerator, or the denominator is higher than the numerator. So here we're going to have a horizontal asymptote at y equals 0. Okay? So that's an interesting one. You can actually see there's a horizontal asymptote there, so there must be a hole at 0 that this horizontal asymptote passes through. Okay? So let's get to the summary here. It should make a little bit more sense. We've gone through most of it. Okay, the quotient of two polynomial functions results in a rational function which often has one or more discontinuities. Okay, rational function. Remember, no square roots, whole positive exponents. Okay. The breaks or discontinuities in a rational function occur where the function is undefined. The function is undefined at values where the denominator is equal to 0. As a result, these values must be restricted from the domain of the function. So, these values could be a number over 0 or 0 over 0. Okay? If it's a number over 0, we have a vertical asymptote. If it's 0 over 0, we have a hole. The values that must be restricted from the domain of a rational function result in key characteristics that define the shape of the graph. Okay, that goes without saying. If there's a vertical asymptote, it's definitely going to, affect the shape of the graph. These characteristics include a combination of vertical asymptotes and holes. They're also called point discontinuities. Yeah.
You had mentioned for one of the examples, I, because 3 is a constant, there wouldn't be any vertical asymptote though.
That's right.
But it just says there a number over 0 would make a vertical asymptote.
Sorry, did I say vertical asymptote or a hole?
You said vertical asymptote.
Okay. So there could be a vertical asymptote there, but not a hole.
Oh, okay.
So my mistake. Gotta check the tape on that one.
Maybe I heard you wrong.
The end behaviors of many rational... I think you're right. I think I did mess that up. The end behaviors of many rational functions are determined by either horizontal asymptotes or oblique asymptotes. All right. Here, I need to know. This is the important stuff, right? This is the takeaway. Okay? I apologize. It was a bit of a messy lesson. The rules are easy to kind of remember and to recognize. They're tough to develop, right? As you can see, we used 8 different kind of complex polynomial functions.